Start with ED319, which is kind of a long, complicated project, and I just got everything working. So what you have to do is you have to have a Windows target, and I'm using Windows on Intel. An interesting question is, could you do this in Windows for ARM? And I think probably not, but I'm not sure. I would like to add that to this project, but I haven't tested on Windows for ARM yet. But I did get it working on Windows for Intel. So here's my Windows for Intel, and we're going to use Vuln Server, which we've used before. And there's quite a bit in this project about installing tools, but remember, if you're using my pre-made machine, all the tools are installed. Immunity and the Mona had onto Immunity, and the Vuln Server is already there. So you just have to launch Vuln Server and run it inside the Immunity debugger. So I've already loaded it, and I run it. Now my machine is listening. And it's, if you're using a Windows 10 or 11 machine, then the security measures that would block this attack are already turned off. Microsoft only turns them on server versions. So run your vulnerable server, and you should see it here running. See, not there, but here, I guess. Yeah, there it is. Vuln Server, waiting for client connections. All right, and so I've got a series of attack files here. Let me make this bigger and move it to an area that's not going to be blocked by my face. All right, so the first thing is find EIP. I guess I call it find SEH. Okay, fine. So what we're going to do here is I'm going to just connect to my server on port 9999 and the IP address I've already corrected here for this network setup. And so I send 3530 A's, and then I just send 0 through 9, a non-repeating series of digits, because I know the buffer overflow will be somewhere in that area. And so I'm going to run this and send it to the server. That's find SEH. Okay, so it sent it to the server. Now if I look at the server, it has crashed with an access violation when writing somewhere. And it's not immediately obvious that I control anything. But what it's done here is I have overwritten the exception handler. So an access violation occurred. So it's trying to call the structured exception handler. And if I view the SEH chain, I'll see up here, there's 34, 34, 34, 35. That's the digits 4445. So some of the data I sent ended up in the exception handler. So now I know how to control the box. I can create an exception, and when it tries to process the exception, it will go to an address under my control. So I'm going to go back to the CPU window, debug, debug restart. Okay, and yes, and then run it again so it's ready. So now I want to hit the EIP directly, and so that is hit EIP. All right, so now that I've done it, I just figured out that 3547 is the number of digits I have to add to get to the parts of the non-repeating string, and then I add BCDE, and then enough X's to keep the total length the same, which is 4,000. So if I run this one, hit, then I go back to here, and see now again I have an access violation, but if I view the structured exception handler, now it's 42, 43, 44, 45, which is BCDE. Now, let me check my instructions here. All right, now we want to observe the exception handling. So what happens is, when you have an exception and you're running in a debugger, that's called a first chance exception. And the first thing it does is return you to the debugger in case you want to debug it. But in this case, I want to let the program use it. So I'm going to return to viewing CPU, and I'm going to press Shift F9 and on Mac it's Shift Function F9 to resume execution, passing the exception back into the program. So I do that. Now it's going to crash when executing 42, 43, 44, 45 because I know the first value in the exception handler was corrupted. But the reason I did that is because now I can make a plan how to exploit this. And the interesting thing is if you look on the stack, here's the return to some Windows library, then there's some data, then there's a pointer to data, and this is the data I sent in, AAAA, here's the BCDE that ended up in the exception handler, and here's the X's I padded my exploit list, my exploit with. So this means if I can find code that doesn't move, that does pop, pop, return, it will go to this address where these 4 A's are. So now I can redirect execution to something under my control, even though address-based layout randomization is happening, and I don't know where my code is. So I need to find pop, pop, return that doesn't move. And you can do that with Mona. You can run Mona modules as we've done before, and you'll see what defenses there are on the various modules. And you want rebase equal false and ASLR equal false. And you want safe SEH equal false. So you see rebase, those are the first 3 columns here. So you can see ESS function.dil has the property of all 3 of those being false. And vuln server itself has all 3 of those being false. But vuln server loads at 400,000, so all the addresses have null bytes in the middle of them. So I can't use that, so I got to use ESSfunc.dil is the only thing that's going to have it. And now I can run a couple Mona commands to find the addresses in ESSfunc.dil that contain stack pivots. And so when you look at it, it will tell you there's places where there is a pop-pop return. There are quite a few of them, and they're all just fine as long as they don't contain null bytes. The first one is fine, 6250 10B4. So we can take a look at that, 6250 10B4. If I restart the program here and get back to normal, debug restart, yes. All right, now I can right-click, go to expression, and it should still have it there. Yep, 6250 10B4. So I say OK, and there you see pop, pop, return. That's what I want. So if I go to this address, I will find the code I need to jump back and hit the last 4 A's in my exploit. So that's good. So that's what SEH2 will do here. So let's run this program. All right. And let's look at SEH2. All right, so what this does, might as well make it bigger, is it has the right amount of prefix, and then where I had to put in BCDE before just to make sure I was hitting, I put in I put in a shell. This is the 4 bytes, nop, 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 int 3, and here's the address, 6250 10B4. So if this works, it will jump to that address. It will then jump back to the last 4 A's, which are here, and this will be my little tiny toy exploit that does 3 nops and then an int, just so I can show that I'm able to hit this address and I'm able to execute code at that address. So I run this, which is SEH2. All right, now I've got the access violation, so I do shift function F9 to move, and now it goes forward a bit and hits an interrupt because I left some, and you see here that it worked. I processed nop, 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 int. So it did work. It bounced. This is a trampoline attack, the simplest case of return-oriented programming. I bounced off a couple of code to come back to code under my control, and now I'm executing that code on the stack. So that's cool. And, you know, that's enough that you see the essential part. And there's more here that you can do. For example, the one problem with this, remember we've done exploits before where you had to have like a couple 150 bytes to put in something like Metasploit shellcode, or 500 or 600 bytes. Here I got 4 bytes. So what can you do with 4 bytes? Well, what you can do is you can move somewhere where there's more bytes. And it turns out you can't even do it in one step, because even jumping, say, back 300 or 400 bytes would take a 5-byte command. So what you have to do is you have to make a small command, a jump rel 8, I think is the one. Yeah, jump rel 8. This will jump, can only move 128 bytes, but the command is only 2 bytes long. So you have to first put in 2 bytes there that will jump back by a larger amount. Then you can get to where there's a bigger jump to jump back by a pretty large amount. So you end up with 2 commands here, and there it is. You put in this will jump back 10 bytes, and this will jump back 450 bytes. So you have to put in both of those. So your attack gets a little complicated. You have the prefix, Then you have the jump 450, the jump 8, and then the pivot. So this pivot will jump to a pop-pop return, which will jump back to this one. This will jump back 8 bytes, enough to get you to this long command, which will jump back 450 bytes, which will be back in early part of all those A's I injected, and then you can inject code there. So I don't think I'll bother doing it. It's pretty fun. It's an exercise, but you get it working, and I got it working right before class. You can test it, and then you can do the same thing before, generate Metasploit shellcode, and have a whole reverse shell. So that's what I wanted to show you, and there's stuff to do there. And if you get it working well enough, you can then exploit my real server that's running in the cloud remotely, which is pretty tricky, and you will have to have a public IP, like a Google Cloud machine, to do it. But it's a very realistic attack. All right, so that's what I wanted to show you about that one. Let me stop the recording.